Hello.
Hi. Okay, welcome back, everybody. Hope you had a wonderful networking breakout session. Sarah, so glad to see you. Thank you so much for joining. We are going to kick off this block with your presentation, and you're going to be talking about achieving a $2 per pound metal additive. And I'm excited to hear all about that. So I'm going to start recording your presentation, and you can share whenever you're ready.
All right. Are you seeing my screen now? All right. We're ready. Let's go. All right. Well, thank you, everyone. My name's Sarah Jordan. I am the co-founder and CEO of Skuld LLC. I suppose I ought to give a warning in that there's a good chance that this talk's going to make some of you disagree, prompt some thought out there. A colleague of mine starts his talk saying, if I don't make at least half of you mad, then I've had a failure to communicate. But first, a little bit about myself. I am a metallurgical engineer with over 20 years in a range of processes, including casting, heat treating, and of course, machining. I also have been working in additive for going on about 7 years. About 13 years ago, I went over to what my husband calls the dark side, aka the business side of things. I have an MBA from Carnegie Mellon University, TIPE School of Business, one of the top business schools in the world, and one of the top business analytics schools. After I graduated from there, I spent 4 years as the forecast manager for a $1.5 billion business unit at Emerson. I used to say that my job there was to make up numbers, and then I moved to a supply chain role where I made decisions with those numbers that I got from my successor who I had trained. So then I said my job was to make decisions with the made up numbers. Anyways, between those roles and working at 6 prior startups, including 2 I co-founded and 2 I partially own, I have a pretty extensive background in thinking about forecasts, business planning, and costing. We will get to the money side of things in a bit, but I want to talk briefly about forecasting. So first, anyone who uses forecasts should be aware that when predicting the future, that even when you're given a specific number, it really is a probability distribution. So if you think about basic statistics, if you're gambling and you get $1 for every time it comes up heads, we'll forecast that you'll win 50 cents on average, but really you have a 50% odds of winning $1 and 50% of winning 0. Forecasting is kind of like that. In that, a forecaster will give you some line out into the future, this gray line, but realistically, there's some probability distribution where, like, if they gave you a range and say, okay, they're 50% confident that it'd be between these yellow lines, or they're 90% confident it would be between the blue lines. Actually, forecasters know that if you have to give a point number within a probability distribution, that actually the probability of that specific number occurring is close to 0, and that's why forecasts are almost always wrong. So, which comes to my next point, some things to watch out for in forecasts and why you shouldn't blindly trust them, including the things I'm going to tell you later in this talk. First, there's always error. That's the difference from the prediction and accuracy. So, this should be something or is reported, but often isn't. Bias is the systemic difference between if somebody's constantly predicting high or constantly predicting low. There's often politics involved, and I don't mean by this the government, I mean interactions with people. So often there are things that are influencing the impartiality of the forecast, such as who's the forecast for, what your boss is telling you, what the pack and general consensus is saying. All of these things can influence the forecast. Another thing that matters is what's the purpose of the forecast. So forecasts made by financial analysts on Wall Street have different purposes than if you're trying to predict the market for your own company or trying to justify purchasing equipment. Another key thing that is often not noted in forecasts in the media is what are they defining the market as? So thing I've noticed is that often in the 3D printing market, they'll group all kinds of things together, such as parts, service, materials, equipment, and it's not always clear what all they are including. Confirmation bias, that's you wanting to believe the forecast because it already fits in what you already think. And then finally, the thing to watch out for is the S-curve. Go into that a little bit more. So if you saw this curve, which looks pretty similar to the current history of additive manufacturing, where would you draw the line next? You might draw it like this red line, right? That makes sense. You're just extending it in the future. And if you're going to use time series modeling software, that's pretty much what the analytics are going to tell you as well. They're just going to be like, oh, extend that line. Well, the problem is, in this case, the left axis is actually market fraction, and it's the percent of the market who wants one, who has one. And actually, with market fraction, the maximum that you can have is actually 1. It goes asymptotically to 1. So the line is going to curve over at some point. At some point, everyone who wants a 3D printer will have one, or maybe they'll have more than one, but they'll have what they need. At some point, people who are going to adopt new parts, they will have done it. So at some point, this is what will happen to the growth curve. It's not going to go up linearly forever. Now, just so you don't think this is a theory, here's an example from an actual product that most of us are aware of, and many of us have on our pockets right now. And this is the Apple iPhone. So it went up fairly linearly for about 8 years, and then it actually dropped off before leveling off. At that point, people are just, for the most part, replacing an existing older model. Most of the people who would like an iPhone have one at this point. Now let's look at some forecasts for additive manufacturing. These forecasts are all pretty much going up, and it's pretty clear that no one is considering the S-curve phenomena yet, and that these things might taper off at some point. In fact, some people, like this pink line, are predicting exponential increases in the future. If you look out at the year 2026, there's a really wide gap between the lowest and the highest, about between $20 and $70 billion, give or take, which is actually a pretty huge range if you're trying to make decisions with these predictions. Now, since I'm in metal 3D printing, I think, I wanted to look at what are the forecasts in that space, and they're pretty wildly different as well. This is for parts, not printers themselves. And there's predictions anywhere between $2 and $16 billion by the year 2028. Now, most of these people have pretty high compound annual growth rates, between 23, 30%. But you can also see that they have different starting points, because if their history is so far off, that they do have slightly different market definitions here. But they are wildly different. So, which brings me to my next point, and that when you're predicting the future, this may seem self-explanatory, but if you're assuming there's going to be some kind of technology developments, then you're going to get a wildly different result than if you're just assuming some kind of market adoption of the existing technology. Now, when we talk about additive manufacturing for parts, some of these are new to the world parts, but some of these are consolidating other existing parts or making designs that, could be made in other processes. So the question really is, what do we expect the ultimate available market to be for metal additive manufacturing? And to some extent, this is going to depend on how far the technology advances. Now, I saw a quote last year that said if metal additive manufacturing could achieve $5 a kilogram, then it would be a $100 billion market. Now, on one hand, that seems like an incredibly huge increase compared to the forecast that I just showed you. But on the other hand, it seems reasonable because that gets the price down below machining and in the neighborhood of formative processes such as stamping, casting, and other mass-produced parts. But that's a big if, getting down to $5 a kilogram, or for those of us in the US, $2.27 per pound. Now, for the prior 3D printing forecast, it's not clear. What are they assuming? What's the basis for their forecast going out 7, 8 years. Are they assuming an improvement in technology from the current state? Are they assuming big drops in costs from the materials and equipment point of view? And my guess is probably in a lot of cases. If they just expect metal AM to win market share, it's really not clear where they're expecting it to come from. But in some cases, they may just be extrapolating past growth trends into the future. So I want to try to go through some costs, analyze the costs of the current state, and analyze where we would need to go to get down to that $2 a pound goal. So this is some basic costing assumptions. It's going to be very basic math. Hopefully it's not too boring, but I'm going to go through this pretty quickly with a generic part. So if we look at powder bed fusion, and these are my assumptions, and you might disagree with them, and that's okay. You can redo this analysis and make different assumptions with your own numbers if you want. But I'm going to assume aluminum, and what are we going to start with is a reasonable powder cost. Now, obviously, powder costs can really vary depending on your assumptions, but I've picked $40 a pound, which right there we have an issue if the total cost of the part is desired to be around $2 a pound. Now, if we look at labor, if we assume $15 an hour and, reasonable 50% is going to various benefits and taxes, that gives you an employee cost of $22.50 an hour. Now, these machines print relatively slow, about, let's assume, a cubic inch per hour. And based on the density of aluminum, we can calculate that you're going to need 10 hours to get a 1 pound part. So we know these machines are automated, and the person doesn't necessarily have to stand there the whole time. But I make the assumption that for this 10 hours that you're going to need 30 minutes of labor, or 11.25. Similar analysis can be done with, how much is the time for the machine going to cost? So, machine prices can be all over the place, but if we assume $100,000 and we divide this by 10 years for straight line depreciation, and we're running this 24/7, you can get a cost to operate a machine per hour. In this case, $114, and if it's again 10 hours to print a pound, then right there the equipment cost is going to be $11.40. Now, for comparison with some of the mass production rates, this is less of an issue. For instance, I got an aluminum melt furnace quote recently, which is $90,000. But the difference is that equipment makes 1 ton an hour of material. So doing the same analysis, it actually gets you a cost of 5 cents for the machine for 100 pounds of material. So it's pretty negligible in that case. But for 3D printing, the depreciation of the machines is a big deal. Next, we have post-processing. So those can be all over the place. But if I assume that we're going to ignore heat treating and basically just looking at support removal, the machining that's needed, I, in this case, just decided to assume 10% was a reasonable amount for machining. We get down so that the total, just adding up these basic costs, that the material cost is, about $70 or above 30 times our target goal here. So if I do the same kind of analysis with binder jetting, again, it has raw material costs. Now, in this case, they're a little bit cheaper, and binder jetting does have a somewhat higher production rate, so it's going to take less labor to go into this. It produces more pounds per hour. That part of it is actually directionally correct in getting the labor and the raw material costs down. However, we run into a different issue in that binder jetting tends to have much more expensive equipment. There's multiple pieces of equipment needed, such as for sintering as well. And I'm told that these typically run about $1 million. So if we're going to do the same kind of straight line depreciation for 10 years, that actually gets us to $11.42 an hour, or $4.45 per pound. I know that thinking about things on a per pound basis is not the most common thing, but if you depreciate faster, you'd actually have this per pound cost go up. But on the other hand, maybe you can ramp up your production rates to make it go down somewhat. But still, you're already well above this target. Now, post-processing in metal binder jetting is a little bit less because they don't typically require support material unless they're trying to deal with any kind of sagging during sintering. And it is a fairly accurate process, but I'm going to assume in this case 4% cost for post-processing. So 1757 is my rosy scenario assumption here, and it's still a fairly long way for the target, but it is better. Next, people might have asked me about sand printing because casting is considerably cheaper. So in that case, if you just are going to look at the ingot metal costs, yeah, that is cheaper, $1.25. The problem is that when you print for sand, you actually have to print a good bit bigger part than the space you want. So if you want a part that's very simple rectangular prism, 1 by 2 by 5, you actually have to print a mold that's substantially bigger, and that actually means you have to print, in this example, 260 cubic inches of sand. So even at a very cheap 7 cents per pound, which I believe includes the labor and equipment and margin in there, that actually gets you $18.20. So right there, again, it's gotten way beyond what the target is. I need to add in this analysis some labor for the foundry itself, as well as the other issue with sand printing is tolerance control. So coming from a foundry background, sand casting actually has pretty poor tolerances. The molds tend to erode. Silica sand undergoes a phase change at high temperatures, which causes them to have tolerances that vary about 3%. So most sand castings get a lot of machining. One example, foundry part I looked at recently started at 5 pounds, and they actually remove 1.5 or about 30% of the weight. And that gives 2 problems. So basically, first, there's the machining cost itself. And then second, you're throwing away metal, which means you have a certain set cost, and you're actually dividing it by less weight for the final finished part. So in this case, I assume 20% post-processing costs. So again, the total cost in this analysis, $24.34 a pound, or about 10 times above the target. So if we're trying to get down to below $2 a pound, so far, are you depressed yet? I actually consider some of these to be kind of rosy assumptions, and we're still an order of magnitude away, and this is just for costs. So something to point out, costs are what you pay for something, but price is what you sell something for. And customers, they're looking at your price, considering it their cost. So none of this includes a whole host of other costs of being in business, let alone profit. So how do we get out the cost from this? Is this $2 a pound goal even possible? So some approaches to lowering costs fall in one or more of the following categories. So there is a bit of a problem here. Some of these, if you positively impact one, then the others negatively get impacted. For example, faster print rates, that can be done with more lasers, but that tends to negatively impact the cost of the equipment. And the same thing with labor. If you want to add automation and have less labor, well, that again will increase the equipment costs. The approach I do commonly see with the engineers in additive is having clever designs to help drive down the cost, whether this is lattices or printing in certain orientations. There are all kinds of things being done in the additive manufacturing world to try to get the cost down through clever designs. Now, I do want to talk briefly about my own company, my startup, Skuld LLC, and my PhD research, because what we are trying to do is approach this problem and address it to get additive more affordable. This new process, which I just kind of give a quick overview here, is called additive manufacturing evaporative casting, or AMEC. I'm not going to go into any of the technical details really, but if you want to talk to me about it after the talk, let me know. And how does this approach compare? So for raw materials in this case, we are actually, again, using the foundry ingot prices, $1.25 as I previously mentioned for aluminum. And then we 3D print using basic FDM polymer filament. So that's pretty affordable for raw materials. Next, we use minimal infill, so it takes less time to print. And then we use much cheaper desktop printers, which have a pretty trivial amortized rate on a per pound basis, as well as if you need to speed things up, you can just get a wall of printers like some places do. And finally, from a post-processing standpoint, this process is based on lost foam casting. So it's about 0.3% accurate and needs much less machining. Now, the labor on this does need some work. Right now, this is a medium TRL process, and it's not quite yet ready for being in high production. But at some point, that would be possible to get this more automated. Right now, the labor that requires about the same amount of labor, whether we're making a 1 pound part or a 40 pound part. But looking at these assumptions, and kind of similar with the assumptions before, we actually can get a similar kind of costing for AMAC. And in this case, as I said, the raw materials, much less. The labor, and this was, I did this analysis assuming a larger part so we could actually get the labor down. Otherwise, the labor would be much higher if we were looking at a 1 pound part. The equipment is very negligible, and post-processing, this has been scaled down to be similar to the above rates. So again, $3 per pound is not quite there yet, but it is definitely getting closer. And I think that this process, if we actually weren't looking at aluminum, if we were looking at something like A36 steel, actually you can take out a good bit of the cost from the ingot prices. So I want to show you the level of detail that's possible in AMAC. This is actually a zoomed in on a metal aluminum part, and you can actually see the 3D print striations they carry over from the polymer. And this is about a 1/2 inch wide section blown up here. But it does show you the kind of the level of 3D printing detail that's possible. So to wrap up my talk, I want to give you some predictions on where I see the additive market going. I actually think that the market is bigger than some of even the most optimistic forecasters think. I think that $2 per pound is really not crazy. But of course, sales price depends on value, not cost. And people will try to charge as much as they possibly can to sell parts. I mean, that makes sense, right? I think that the implications of metal AM dropping to a point where it's competitive on price with traditional manufacturing are huge. The amount of things that can be customized will go up a lot. But this will have a headwind in that the impact of those non-recurring engineering costs will become something that matters. And I've really totally ignored that in all of this analysis here. Finally, right now, a lot of cases people use AM for prototypes or very, very small volumes. But I think that the point at which justifying tooling is going to shift towards higher numbers. We think somewhere between 5,000 and 10,000 pieces. Above that, tooling would probably make sense. Below that, maybe it doesn't. Of course, this is going to depend on if you're using additive manufacturing to make part designs that aren't possible in other means. So in which case, you will not necessarily make tooling at all. So with that, I will thank you for your time, and I will open it up to questions.
Thank you for sharing your presentation, Sarah. It was fascinating watching you crunch numbers. and really, really cool to get an insight into what you're doing at your company over there. So I'll just throw it out to our audience. Did you agree or disagree with Sarah? What did you think of her forecasts? We can definitely discuss more on the networking site. So if you catch Sarah over there, then go ahead and feel free to argue with her, right?
Yeah. Part of this is just make people think.
Absolutely. Absolutely. Thank you so much for sharing. We'll see you later on in the conference.
Yeah. All right. Well, thank you.
Bye. Okay, welcome Jillian from Hummingbird Additive is our next guest speaker. We're excited to have you, and I'm going to give the floor to you to present.
Great, thank you very much. All right, there we go. I've got the screen up. Well, thank you all for joining me today. I'm excited to talk to you about expectations versus reality. This presentation will cover expectations versus reality encountered throughout the production lifecycle. And that lifecycle will be from prototyping to scaled production. The talk's intended for project managers to help you navigate expectations and forecast reality into your project planning. Before we get started, a little bit about myself. I'm the co-founder of Hummingbird Additive, where I focus on metal AM strategies and applications. One of the things that I like best about my role is getting to develop new capabilities with clients. And in order to do that, it's helpful to understand common expectations. So with that, let's dive in. The first expectation we'll discuss today is quantity. Quantity increases with production maturity. That makes sense. The second expectation is that labor will decrease over time. And this decreases as production scales. I want you to notice how smooth these lines are. These are the expectations that are common. But then there's reality. It's not actually that simple. So this is more of what a production life cycle really looks like. You'll see all of the different variation, and we'll go through what the different peaks mean throughout the presentation today. When you transition from one phase to the next, it'll require the most effort from your project team. And each phase has its own unique challenges to overcome. When you overlay cost, you'll see that cost is a lagging indicator of effort. So your production costs will increase until both your manufacturing and engineering inefficiencies are addressed. There are 4 key decision points throughout this production lifecycle that we'll talk about today. We have building prototypes, starting qualification, beginning production, and ramping up production. And we'll talk about the different questions you'll need to answer before you can proceed through each of the 4 gates. So let's start by looking at prototyping. Before you can pass through the gate to begin prototyping, you're going to need to answer a variety of questions from both your executives and your engineers. Keep in mind that executives want project definition, and they'll ask questions like, what is the cost benefit? Can we make a business case? And what level of investment is needed? Engineers are focused on product definition. So they'll ask questions like, how does AM compare to our current manufacturing method? What are the realistic feature tolerances? And what is the expected performance benefit? Once you've answered all of these questions, which are both sets are important, we'll be able to proceed through the first gate and start building prototypes. So once we have the funding, we'll be able to develop our requirements. These will cover the form, fit, and function for our product. Once those are defined, we'll build, test, and iterate. And we'll continue to build, test, and iterate until we have our test results that show that our performance meets our requirements. When you're prototyping, be aware that rarely are legacy designs AM ready. You might even have inherited a legacy design that doesn't have a CAD model. So wherever that legacy design begins, you'll need to update it so that it is compatible with additive manufacturing. Keep in mind that your production unit price might be higher than your prototyping unit price due to the different quality requirements that you'll need to add. And during this phase, you'll be asked a variety of questions, many of which are forward-looking, about the product life and the production unit cost. But prototyping alone won't let you accurately answer these questions. You'll need to wait until the next phase, qualification, before you can answer those. Prototyping is a time where you can spend time and effort just making sure you have the right material and technology fit for the capabilities that you need. Reminds me of a project that I joined. I joined after we ordered the first prototype. When we received that in, found out that it just didn't meet the performance requirements, which was a bit of a surprise. But we took a step back and decided to actually iterate the design and build it the second time using a different additive technology. When we received that prototype back and tested it, it not only met our performance requirements, but it also came in lower cost and with a shorter lead time. So prototyping is a time where you spend the time and effort to really make sure that you're coming up with a project that is worth taking to production. Now let's look at production. This phase has two gates. Gate 2 is starting qualification, and Gate 3 is beginning production. Before we can start production qualification, it's important to define our business case. What is the expected ROI? What are the time and resource investment needed? And what are the benefits to the bottom line? In addition to these items here, executives will ask forward-looking statements. When can we start production? And how do we market the product? It's important to keep your eye on the road ahead so that you can be prepared and have a market ready and waiting for once you're ready to start production. Before you can proceed to qualification, your engineers, who are again product focused, will ask questions like, what types of test data are needed and how many samples do I need? This is going to be highly dependent on both your application and your industry. They'll also ask, how can we mitigate risk? And are all of the production operations well defined? Once you've answered all of these questions, there'll be time for you to start qualification. So once you have the funding for qualification, you can create an initial procedure and your quality control documents. This is where you'll be spending the time to validate your technical capabilities by building qual units and test specimens. Once you have all of that data and you've analyzed it, you'll be able to go back and finalize your requirements and your procedures. You'll pay special attention to identifying key product features and metrics, as well as establish your inspection and pass-fail criteria that you'll use during production. During this phase, you'll also start to build trust with your stakeholders and your key customers regarding the product's quality and performance. And since we know that unit cost is a lagging indicator of effort, we're going to keep our eye on that unit cost because it will be rising as we add quality requirements. By taking the feedback from your stakeholders and key customers, as well as knowing that your unit cost will rise, you'll be able to go back and validate your final business case and technical case and send it out for approval. But before it can be approved, we'll have a few more questions to answer. Executives, again, want more project definition. So they'll remember that they asked you ROI targets back at the beginning before you started qualification. Now they'll want to know, did you hit those targets? Will this product hit all of our ROI targets? And then how have the risks been mitigated? And finally, when can the production rollout begin? They're again going to be focused to make sure that you have a market ready and waiting for this product as soon as it's ready to begin production. Engineers will want product definition. So does this product meet its performance requirements over lifetime? What is the unit cost and lead time? And what is our expected production yield? Once you've answered all of these questions, then you'll be ready to begin production. So now that we've entered production and you're in your first run, you'll see that the unit cost is increasing again because production's an evolving process. You'll probably find some additional requirements that need to be added. They only find out kind of when you're in the thick of it. Your unit cost will actually peak probably around your second or third run. This is after you've stopped adding additional requirements, so those are all locked down. And then you have found and identified the manufacturing inefficiencies. And perhaps you've taken into account previous underestimates and have everything more clearly identified now. You'll see that in your subsequent builds. This is where you can iron out those workflow inefficiencies that you identified. And as you do, the unit cost decreases accordingly. When in production, be aware that it's an ever-evolving process. You might have changes in personnel or a new vendor that you have to work with, and throughout this whole process, you'll be incorporating your lessons learned. One thing to keep in mind is that post-processing operations may be more of a cost driver than printing. Let's consider surface finishing as an example. Let's say your legacy product that you're carrying over was originally machined, and you just inherited the requirements that that part had. You might actually have machined tolerances and machined surface finish requirements that are in your initial baseline requirements. Well, as you all know, additive manufacturing can't actually achieve machined surface tolerance, machined surface finish and tolerancing. So you'll need to look into post-processing operations to meet those requirements. And some of those can be pretty expensive. So taking the time right in this, when you're defining your requirements, to understand what your actual requirements are for the product will allow you to find out if you need additional costly post-processing operations, or if you're able to eliminate some of those steps. Either way, come up with your realistic acceptance criteria, and being able to do that will balance the unit cost with your real product requirements. Throughout production, if you're making changes and incorporating lessons learned, keep in mind that any changes that you make to your processing steps might nullify previous risk reduction activities. So just keep that in mind. You might need to do some additional testing before you make some changes. At this point, if you're able to create a scalable manufacturing strategy that you can use and test out during production, that will provide you with many more options for future growth. So next, let's look at scaled production. So before we can reach scaled production, we have studies to do. We'll need to decide exactly how we want to scale production, because there are several different options. We'll evaluate the benefits of using a larger AM system versus adding additional systems that are similar to the one we're already using. Once we've done those trade studies, we'll also be scrutinizing our workflow, and we'll see what areas we can standardize and streamline so that we can address our bottlenecks from printing all the way through post-processing. Here we'll refine our acceptance and inspection criteria based on historical data, keep in what helps, and remove any unnecessary steps. And then we'll wrap all of that up and create an updated business and technical case for approval. Before we can scale, we again have a few more questions we're going to need to answer. Executives are going to want to know what the market projections are and the ROI for scaling production, what investment is needed, and then again, that forward-looking statement, when will the additional capacity be online? They'll always be keeping an eye on the future to make sure that they have a large enough market ready and waiting for the capacity as soon as you have it online. Engineers will be product-focused, and they'll ask, what's the impact of moving to a larger system? How can we improve our production yield? What effort is needed to validate the new systems and our facilities? And what further risk mitigation activities are needed? Once you have all of these questions answered, you'll be able to go through the fourth gate and start scaling production. Now, once you start scaling, you'll be qualifying either new equipment or qualifying new facilities. Either route you go, you'll be taking that test data and verifying it against the benchmark data that you've gathered during production. You want to make sure that your quality in scaled production meets the same level of quality that you had during production. You'll notice that again, since cost is a lagging indicator, you'll get a bit of a bump in your unit cost. So if we look at the solid green line, this is a lower increase in unit cost because in this instance, we went with adding more machines and more personnel, but not changing the facility. So we already have staff that have learned those lessons throughout production with us. The second option is if we decided to bring a new facility online, and they have a bit more of a steep learning curve to catch up with all that we've been learning throughout production. So you'll have a higher spike in your unit costs represented by the dashed green line, but you'll see again that that will start decreasing and they'll both come back down to steady state. So long term, we know that there will be market fluctuations. That's just a fact of life. So maybe between one order and the next, our powder costs more, or perhaps the price of gas has gone up. Either way, we'll have relatively uniform unit cost, but it will have some fluctuations. During the sustainment stage, we'll have our steady state effort to maintain our scaled production. So when scaling production, be aware that it takes longer and more investment to bring less experienced manufacturing operators online. It can be pretty easy to overwhelm a new supplier, so start small and ramp up. I've had the opportunity to be on a number of facility audit teams, and it's always interesting how different some of the facilities can be. I'll go into one facility and I'll be really impressed with the knowledge of the people, the detailed processes that don't have any gaps, and the training regime. I'll feel completely comfortable that if they hire someone new who goes through the training and then has access to the processes, that they'll be able to maintain the current level of quality that the facility has at the current production level. Unfortunately, I've also audited facilities where that's not the case. We'll still have incredibly skilled people, but the processes have some holes. And so it's easy to see that the level of quality that's there today is just because we have some really sharp people in key roles. But what happens if they get sick or they decide to change companies, or so many new orders are coming in that a lot of new personnel needs to be hired? When you scale in a facility like that, then you have a few more concerns because of the gaps in the processes and or the training regime. So make sure that you really do some detailed reviews of the facility you want to partner with when you're scaling up production, so that you guys can, since you both will be in it together. So when you're scaling production, be aware that you also will need to scale your post-processing capabilities. So don't forget about those. And throughout this whole process, make sure that you keep your customers and stakeholders informed, as this builds trust. And this will allow them to be ready to accept your new quantity of scaled products as soon as it's ready to go. And finally, keep in mind that consistent build layouts drive production efficiencies. So what I mean by this is, if you are sending the same quantity through your orders, same recurring order quantity, then it's going to be really easy for the manufacturer to reuse their build file. They're not going to need to spend the time and labor to redo that and then retweak their processes and travelers. And that lack of touch labor, let's say, will actually be reflected in your unit price. So the more consistency that you can bring to your scaled production, the more efficiency and the lower the unit costs can be. Lessons learned throughout this product lifecycle will help you jumpstart into the next one. So keep in mind that in reality, your next project may not wait for you to finish the first one. So it's really important that you incorporate your lessons learned as you go. So it's important for you to address the expectations. Feel free to use this presentation and share it with your executives and your team so that they'll be clear exactly what questions you'll be able to answer in each phase of the production lifecycle. Make sure you discuss the project expectations with your executives and your team early and often. Forecast reality into your project planning, and communicate realistic product expectations with stakeholders for a smoother adoption. So while you address the expectations, make sure that you prepare for reality. Now that you have a better understanding of how the process really works, that understanding will be able to be the foundation for your future success. Thank you, and I hope that you have found this presentation helpful. I'd be happy to answer questions.
Jillian, that was a lot of great content. Thank you so much for sharing. Apologies.
Afraid I lost you, Lindsay. But I see some of the questions, so I'm going to go ahead and answer a few. Hopefully, I'll just go in the order that I see for the votes. The first question that I see is, what are challenges organizations often take for granted when embarking on AM? One of the things that I've noticed is that sometimes people don't quite understand that there is variation from machine to machine. So if you're in an industry that has, such as aerospace or automotive, and you need to have very detailed qualification and data results, you'll need to take that into account. It's not so easy as just pushing a button and bringing that second machine online. There is some investment and labor that's involved to be able to do that. The second question I see is, how do you get executive buy-in? And do the numbers tell enough of a story, or do you need to sell the AM dream? That's a very good question and a tricky one. There's a line that you actually have to walk. You can't sell the dream so much that they're in the clouds, but you need to get them excited for what additive can do for the bottom line. So since they're project focused, walking that line is going to be much more important than telling them how great of an improvement the performance results alone will be, because that won't get them quite as excited as understanding the impact to the bottom line and what it can do for the business as a whole. So I would spend some extra time understanding your business case in and out, understand your company and potentially each executive's individual pet projects, let's say, or the individual things that they look at that get them excited, and make sure that you're able to answer how additive will impact that particular key aspect of the business. And once you've done that, you'll get your executives excited and help sell the AM dream. And the last question I see are, what are the challenges of getting engineers on board? Also a great question. But again, since engineers are product focused, that's where we'll focus on the increases in product performance, increases in freedom for designability. What can we do today that we only dreamed about yesterday? Things like that, and understanding what realistic capabilities are. Because again, you want to sell the AM dream, but you don't want to sell it too much. Don't give false marketing numbers. Instead, spend a little money on prototyping if you can, to find out what the real numbers are for either your tolerancing or your specific features for your product. So then your engineers can be excited and they will dream big. So give them information and the sky is the limit after that.
Awesome. Great questions. Great presentation. Thank you so much, Jillian.
Thank you. Hope you have a nice afternoon.
Hello, everyone. Welcome to the panel. Hey, Joelle.
Hi, Mary. How are you?
I'm good. We'll just wait for Barbara to join us on stage, and then we'll kick it off.
Sounds good. I'm excited.
Hi, folks.
All right. Well, welcome, Barbara. So I'll do a quick introductional. My name is Mary Senosiain. I'm the product manager for Stratasys Direct. I've been in the additive industry for almost over 8 years. I started as an entrepreneur with my own service bureau. Luckily, I now have access to a lot more technologies as part of Stratasys Direct. So Stratasys Direct is Stratasys Service Bureau here in North America. And so I help oversee and manage the roadmap for the customer experience across all 9 technologies that we have.
Awesome.
Barbara, who is joining us, is actually an additive and manufacturing professional with over 30 years of experience. So I'm going to refer to my notes here. Barbara brings a really diverse background to the table. She's championed 3D printing as well as plastic processing, tooling, and other supporting technologies that are very well known. She's published over 70 papers, has won numerous awards, has held quite multiple roles in several organizations, including the Society of Plastic Engineers, SME and Women in Manufacturing, and the Society of Women in Engineers. So her past career actually includes sales, operations management, to be clear, project leadership for many of the injection molders, thermoforming, rotational molding, resins, mold making, tool and die, as well as her experience and specialties in rapid tooling, including stereolithography, SLS, FDM, polyjet, multi-jet fusion, SLM, and high-speed machining. So welcome, Barbara. Joelle is actually joining us from Stanley Black & Decker. She is the Business Development Director. Congratulations, Joelle.
Thank you.
And she is concentrating on operation innovation within manufacturing. And her goal is to continuously bring innovation into manufacturing and increase productivity and ultimately grow the bottom line. Joelle is currently leading a major initiative to bring additive manufacturing capabilities to each of the Stanley Black & Decker locations. So that's over 400 facilities across the world, right?
Mm-hmm.
And she actually began her career in manufacturing, learning the ins and outs of how a facility operates as a manufacturing engineer at Tiffany & Company. So it's very, very unique and very cool in my opinion. And then she later specialized in additive manufacturing and is focusing on how enterprise companies can benefit from leveraging this evolving technology. And Joelle received her BS in Industrial and Systems Engineering from the University of Rhode Island and is also a Lean Six Sigma Black Belt. So welcome.
Thanks, Mary.
Well, it's a pleasure to have you ladies. We're not to say guys. So Joelle, I'm going to start with you. What got you started in additive manufacturing at Tiffany's?
Yeah, absolutely. So like you mentioned, I started out at Tiffany as a manufacturing engineer. So learning about their current processes. They were utilizing additive very early on for lost wax casting and investment casting. So actually printing wax models. And so there was an opportunity that arose to participate in some R&D for additive, see where else we could leverage it. And at that point in my career, I was really looking to be more involved in the business decisions and looking to explore more technologies. So I jumped at the opportunity, and I kind of, it was a happy accident that it turned out to be additive manufacturing because I previously didn't have much experience in it. But that's where my path has led me, and I've been working within additive now since that point. So I clearly like something about it. I love the additive community. I think events like these are great, and there's so many people that have, like Barbara, a lot of different experience, where I would say I'm more so in my infancy with my time within the industry, but I really like it. So that's kind of how I got started.
What about you, Barbara?
I came from an industry that was very, very different. I came from the medical field. So I have actually a degree in biology and clinical medicine. And when I discovered a couple of things that are reality based in that about me, you can't make any money being a bench biologist. So doing Petri plates means that you're very poor all the time. And I had worked my way through college being a tool and die apprentice / machinist to my father. And so I loved making things. That with the ability to go into the plastics industry, because at that time there wasn't any tracks to learn plastic engineering, I was able to enter the world of plastics and get a lot of great experience. An opportunity to join an additive manufacturing company came up quite a while ago. And these guys took me under the wing. They taught me not only about what they had at that time, which was mostly stereolithography and SLS, but also the history of it. And I could see where I'd worked in the industry inadvertently before. I'd actually run a LOM machine, a laminated object manufacturing machine, very, very early on in my manufacturing career. So I somewhat fell into it, but then it was, you might say, a controlled fall, because once I was there, I never wanted to leave. And I still love the industry. I love the tech. In fact, anyone that knows me will tell you I am absolutely a 3D printing geek. I love doing it. I love talking about it. I carry sample parts with me. I believe it can benefit every type of manufacturing. A key for me is to make sure that we know that it's not a fit everywhere, but it has an impact everywhere. So for those of us in the manufacturing world, you have to be selective. But in the old thing from Glenn Beal in the plastics world is that just because you can doesn't mean you should, but you should try in most cases. So that's how I ended up in 3D printing. I've gone through all the technologies. I've worked for major corporations as well as startups. Love the industry and so happy to be here and with a distinguished panel too. Wow. So it's exciting times. It's great times. And it's a great time to be a part of women in 3D manufacturing.
Yeah, I mean, I agree with everything you just said, Barbara and Joelle. And this day, as well as tomorrow, is going to be quite inspiring to everyone involved. I haven't heard anyone say otherwise. Yeah. So let's go ahead and deep dive a little bit into production. You both have experience introducing additive to production life cycles. So right off the bat, in your experience, what has changed once you've implemented additive into the production life cycle? We'll get back to prototyping and that detail in a little bit. What's the first impact right off the gate that you guys have seen? So Joelle, we'll start with you.
Sure. I think one of the biggest impacts of leveraging additive in production is the buy-in from the organization that it's being implemented in. So I've historically and still work with large enterprise companies to implement additive in. And I think one of the biggest hurdles is getting everyone on board with this is a great solution. These are all the benefits from it. It's going to work. So I think right from the start, once you put a part into additive production, it starts changing the way people view additive as a solution. And I think it really drives adoption when a large group of people can see the impact and, wow, it really can work. And I can't believe they're doing it. How do I utilize it? How do I create new products for it? And I think that's been the single most important driver and impact from bringing additive to a production level. Is that education and just opening people's eyes to the possibility.
what about you, Barbara? Coming from conventional manufacturing and then putting an additive into the production life cycle, what did you see change or improve?
I totally agree with everything that has been said previously, because it's an education process and we are on that journey, but we're not at a finish line yet. Mass adoption of additive manufacturing or 3D printing or whatever you're calling it at the time, which I tend to include rapid machining technologies in there too, besides just what we refer to as 3D printing, it still has had an impact in ways that really go back to the concept of what the part does. Instead of just thinking about conventional manufacturing and how we put parts in front of our customers, we're now actually looking at the art portion of the art to part to production and saying, what is this supposed to do? And then going back and designing for additive manufacturing to be put into production. And various technologies are better fits than others when you go into production. I think that's a key to talk to the manufacturer, especially traditional manufacturers that may not be aware of all the technologies. SLS parts, they're a huge difference from SLA parts and vice versa. Multi-jet fusion versus FDM. There's a lot of differences on the strengths and relative fit of those technologies. But the thing I still see now that we're talking DFAM, design for additive manufacturing, that we're actually differentiating it down to design for additive manufacturing within the industry segments into specific technologies. You design somewhat differently for a filament-based additive manufacturing solution than you would for a powder-based manufacturing solution. So we're starting to get that differentiation on the technology. And we also are looking at when additive doesn't fit as a part of the overall solution we're offering. The best innovation is often not a huge lift. It is a hybrid of innovation, new technologies, and traditional manufacturing. And we're starting to see more integration of that. That is huge because now they're seeing it as an option. And sometimes things are, oh, I can do that portion of it in additive. I still need to do this portion, for example, in injection molding. So we're seeing a blending of those technologies, those positionings, and those concepts. That's huge.
So let me ask you this. You guys can pick who starts. Barbara, you mentioned the different terms that we use in the industry today, but you mentioned two in particular, 3D printing and additive manufacturing.
Yep.
There's a very clear difference. I think we agree for those who have been involved in production. But where is the tipping point?
It depends. I've got it tattooed across my forehead. It depends. There's so many factors that go into when it's more economically feasible to do additive manufacturing versus 3D printing. Now, 3D printing, all of us love 3D printing, but sometimes we look at volume constraints as well as 5 major factors that determine whether or not the part itself is being used as a production method versus as a prototyping method. A lot of times it's volume-based, it's cost-based, it's cosmetic-based, it's material characteristics combined with the technology to do certain things to the part. And one of the other ones is just the speed. How fast can you get it, depending on your volume? And all those things kind of mash together to give you a good solution. So the tipping point between additive and quote unquote 3D printing, it's constantly moving a little bit. And I think it's hard to put a line in the sand where, oh, it's now additive versus, oh, it's 3D printing. And you shouldn't say only 3D printing, but it's 3D printing. That line's constantly getting blurred. That line's constantly moving. All of us have worked with craft machines, as I call them. Those are the desktop printers that usually are fairly inexpensive. It's a great introduction to the technology. We all love them. We almost all have them. And thank you for reducing those prices of those so I can have more than one. Thank you. But when you get into doing mass production, and it's different for injection molding versus additive. Injection molding, 5,000 pieces is nothing. But you go to additive manufacturing, 5,000 pieces is a pretty good batch. So you have to define it with your customers on what is additive versus 3D printing. And it's kind of a long-winded answer, but I don't think you can define it. It is defined by the needs of the client, the technology, the materials, and the part itself.
What about you, Joelle?
Sure. I think I have a different view than Barbara. I agree that there's like a blurred line for sure between 3D printing and additive. But working with colleagues that don't generally think about additive manufacturing all day, every day, what I've seen is when we say additive manufacturing to them as a solution, they have no idea what we're talking about. So I almost use those two terms interchangeably because there's a better understanding of 3D printing than there is of additive manufacturing when you say those words to people. So as we're trying to educate and drive adoption, we're leaning more so utilizing the term 3D printing because it's easily understood from the get-go, where additive manufacturing, you kind of have to go into the background of what first of all, what are you talking about? Why is it called additive manufacturing, and so on and so on. So utilizing 3D printing as a term has just proven to be a lot easier, and everyone can jump right into the conversation, having an understanding, maybe not crystal clear, of a difference between FDM and, let's say, binder jetting, right? But they have an understanding of what the topic of conversation is and how it's different from what they're doing today. So I agree with Barbara on the blurred lines, but we're really focusing on just saying 3D printing because it's more inclusive. Especially bringing in people that haven't had experience with the technology before.
No, I think that those are very valid answers. And again, I think it also depends on how familiar you are and what your experience has been within the industry. So going further into the economics, are there specific technologies in your experience? So you both have very different experiences. One, coming from the conventional side, Barbara, are there financial benefits for additive manufacturing? Sorry, no, I messed that up. Are there specific technologies that provide higher cost savings over others? We'll get to that other question in a minute, but
Absolutely. There's certain technologies that are better suited to certain kinds of parts. And it depends, again, tattooed across my forehead. It just depends on, a lot of times, the part configuration and all those factors I talked about: cosmetic speed, durability, finish, and material selection. All those factors play into the economics of when additive is better. On the early part of product life cycle management, one of the best things is that you reach a good design faster. So you have a fail faster type of set when you're doing your concept development. In your production area, you have parts that are many times associated with the manufacturing that are absolutely a fit for 3D printing. And I'm going to use that term interchangeably with additive because, like you, everyone grasps it really quickly versus additive. They're going, well, are you going to talk about digital manufacturing, all that stuff. So let's use 3D printing. Example are fixturing a work cell check fixtures. Great application. Do they work as the part that you're doing the checking on? Sometimes not. Depends on the volume, depends on the part, depends on the size. It depends on what you want to do with it. So there, again, it depends. It's tattooed across my forehead. The biggest factor, I think, on which is the right technology, the right economics of additive versus traditional manufacturing, is going to be very dependent on the part itself. Nowadays, you can make, with 3D printing, parts that you couldn't make with injection molding. Tooling is a big factor. Besides tooling, you've got mold storage, you have inventory items, you have mold maintenance, you have the cost of materials. Anyone that's sourced steel lately can tell you all about inflationary cost of steel. And I'm sure that you're experiencing that at Black & Decker because it's extremely expensive to get raw materials. Additive can be a great fit in there. It also can be a great fit as a bridge production method. It is going to depend on what you've got in terms of delays. If you look at COVID, are there cheaper products out there now versus 2020? Absolutely. You can get a face shield at pennies on the dollar versus what we all were experiencing when we were scrambling to get face shields and personal protective devices. However, 3D printing really stepped in there when you had to have it quick and you couldn't have any excuses about production delays. So it also is a great fit for bridge tooling. So circulus references, it depends, but it is a fit. It also depends on the customer definitions of what they consider traditional manufacturing. 3D printing is becoming traditional. Hybridization is becoming traditional. What we may not have yet, though, is the design for additive manufacturing is still evolving. And we haven't hit our limits yet. So it's going to be a new frontier out there a bit. And we still have to educate so many people about what 3D printing is, too. So long-winded answer, but it depends.
What about you, Joelle?
Yeah.
Do you identify specific technologies that are higher cost savings than others?
Absolutely. I think Barbara was right on with it depends. I think, for example, laser-based systems, the parts coming off of them are going to be really expensive. So it really doesn't make a lot of sense in, let's say, consumer goods for screwdrivers, for example, to make a laser-based product. So I think just the cost of the equipment really plays a big factor, but ultimately it's what are you looking to gain out of the part? Is it being lightweight? Is it really good product or material specifications? Is it really quick turnaround? So there's a lot of different factors that play into where you're going to see the most cost savings. And then there's also a lot of soft factors that don't necessarily get rolled into the part cost, but just saving on material waste, or like Barbara mentioned, the lead time factor. And, during all of these supply chain issues, additive is a really great solution because it's available and you don't have to wait for something to be in front of you from overseas. You can just make it. We've seen that a lot within just the past year. We've been asked to 3D print many things that I don't think were the right fit for additive, but since supply chain issues, we said, why not? Let's take a look at it. Let's see if it's at least around the same cost or less, and can it solve some of our big hurdles with all the supply chain issues going on.
Barbara, you mentioned a little bit about it. Joelle, you kind of touched on it fairly, but what about the man hours? I mean, printing, that's automated, but all the post-processing, even pre-processing that goes in, that's a lot of work. And there's even more work on conventional. Is there a benefit to using one over the others when you look at it from man hours?
It depends. I'm so sorry to keep using that phrase, but in injection molding, for example, you have so many man hours that go into prep, into, you might say, pre-production staging. You have not only design of the part, but you also have tool design, which is significantly different than design of the part. And that's even before you cut steel. You're doing things, you're determining what the tool material will be. There's an old adage in the additive world in that it's called the rule of 10. And I think a lot of us have heard of it. You may have not. I know that Stratasys taught it for a long time. And so it is that whenever you've got a concept and it's on a napkin, if you change the concept, you don't have any cost. But once you put it on a blueprint, you have at least $10. And then whenever you get from the blueprint and you start the approval processes and you start making changes on the fly, so to speak, and this is before you even have it in CAD, you've got $100. Well, then when you put it in CAD, you need to make a design change. Well, I'll put another zero behind that, and you've got at least $10,000 typically when you start to do design changes, and you still haven't cut steel. Once you start cutting steel in production methods, you start exponentially adding cost. The typical mold cost now is you're going to deal with around 3 engineering changes in your molding if you're doing injection molding. Those are prohibitively expensive. The old rule of thumb used to be 5 mold changes, you've got a boat anchor. You really have a tool that's been modified so much that it's compromised. So that is significant cost. But if you go all the way back to design, to find the right design, it's priceless, because worst case scenario, you put a design out on the market that fails and you have a recall. That's an incalculable cost in not only physical product, but prestige and market share. So additive manufacturing, 3D printing, gives you a cost of quality and cost of design assurances that is priceless, because you learn what doesn't work as well as what does. So that rule of 10, it's kind of a general factor in that it's classic project management. When you have a change early on in your project, you have less costs associated with it. The further you are on the project maturation, the higher the cost. If you get done with your project and you have to retrench, retract, redo, the cost is beyond calculation.
Yeah, I think where in manufacturing we look a lot is where we can reduce labor. I think both traditional manufacturing methods and additive have a lot of labor associated with each of them. And our focus right now is where can we reduce touch points where it's really not value added to the end use part. And I think overall, there's a trend within the industry right now to see where can we automate different elements, whether it be putting in a build box or removing supports. There's a lot of technology that's being created right now to support reducing the labor, because ultimately we want to reduce that as much as possible where we can. So I think looking out for those opportunities in both instances of where am I actually creating value for my customer in the end use part, and if I'm not creating value with any touch points, how do I eliminate those? So I think that's something we constantly look into and look at continuous improvement projects and look to limit that in any way possible. So that's something we really focus on.
Are there best practices that you guys have encountered to reduce costs when it comes to additive manufacturing for production specifically?
I think one of the biggest ways to reduce costs is looking at the full downstream processes that have to take place, because there are a lot of great solutions with how you design the part to reduce post-processing or just any other like polishing or anything else that happens to the part. You can reduce significantly through the initial design. So I think something we talk a lot about is taking something that has to be assembled later on and just making it one part from the start. So I think those are kind of a pretty relevant tip of how do we reduce that. Something we've seen also in the industry I'm in is looking at what materials we can utilize. So for example, not needing to polish or plate something after it's produced can save a lot of time and cost just for the product itself. So looking at what's available that currently maybe that material is not being utilized in your industry because of X, Y, and Z. So taking those discovery opportunities to see what else you can use with a new technology like 3D printing.
It's really been impressive when you look at where we are now versus where we were 30 years ago. If you look at what we can accomplish on just plain finishes, wow, it's amazing what the journey has been, especially automation and how much we've automated versus the old day. You know, the Dremel and I are well acquainted with each other on support removal, but now we've got automated post-processing solutions. So looking for that automation, as was said, is a key factor in reducing cost. On 3D printing, any time that you can reduce the number of people that you have to use is usually viewed as a huge cost savings. And the reality is right now in these days of labor shortages, it's hard to find people. So it allows you to not have as many touch points on every project, but more importantly is not look at it as elimination of labor. It's the, you might say, enabling of more projects, because you can put more resources into other areas besides just production. So it allows you to take on more business, and that's a win.
No, and I agree. We recently implemented dimension equipment to our powder bed fusion facility. The automated post-processing equipment is fantastic. It really gives you an end-use part right in your hand within, 24 hours, right? I mean, depends on really the print, but you know what I'm talking about. And you guys mentioned another factor that's very important when it comes to production, which is post-processing. So we've got post-processing as a major factor when it comes to production. You've mentioned material, you said cost, man hours. Is there anything else that's a very important factor when it comes to production, taking into account?
In traditional manufacturing, you always have to make sure there's a good fit between your material selection and the part function. And to get true, you might say, equilibrium of what your demands are and what you can produce, you have to take into consideration what materials are out there. And we've been fortunate in 3D printing recently that there's a lot more materials available than there used to be. You still, however, have a lot of clients that insist on legacy materials, and that they're looking at what they're always been used to versus what the material is really doing for them. And in some cases, this goes back to what criteria the part has and what is the part doing. If you want, a good example is clear. We have a lot of demand for clear parts in additive manufacturing through whatever process is used. The question becomes is, why do you need it clear? Why do you need color? Why do you need this? And sometimes they don't know. They just know that they want it. So you have to balance what's available versus what you might say, the secondary wants and needs. It's almost like an emotional versus logic. Emotionally, I don't care. My car is blue, but I know I want it, so I want a blue car. It's the same thing in parts. It's like, it doesn't have to have, for example, light sandblast finish, but I know I want that. I'm comfortable with it. So sometimes you have to challenge the comfort areas in order to get the true savings, as well as the use and the good utilization of the part in whatever media, in whatever format that you have it going. But another factor is just making sure that you go back to understand what the part is actually going to do and what the critical factors are for use. And I think that's something that you have to go back and reemphasize, that because each layer of management involved in the decision process may have different criteria for acceptance of the part.
I'd also add, for production, one of the biggest elements is quality control and process capability, and ensuring that if you make 100 of the same part, they're all the same. Whereas you can feel pretty confident in that for injection molding, like we've been talking about, but for additive, it's a different ball game. But we still want to be at the same level of confidence that you're going to get the same part 100 times out of the same machine. And I think it takes a lot more for additive manufacturing, a lot more prep work and control planning and initial implementation work to be on the same level as traditional or conventional manufacturing methods. So I would say definitely quality is a huge factor that comes into play of how do you even implement additive into your production environment.
Reproducibility and repeatability is a huge factor in additive. And it's also scale. The scale of production makes a huge difference in your quality assessments.
Yes, and I do want to get into quality. I just want to remind all the participants, you have access to a Q&A if you want to start dropping questions in there and voting them up. We will leave time for some Q&A questions from the participants. But you guys mentioned materials, and we talked about this a little bit early in terms of the product development lifecycle. You mentioned legacy materials, Barbara. Materials are a really important part. They really make up the part.
Yep.
Today, in between that blurred line of prototype and production, is there a clear divide currently between prototype and production materials in your experience?
And this is based on my own personal experience. You don't see very many production parts done in PLA. It's a nice material to use. It's easy to run. It's a great part to use in a prototype setting for form and fit, but functionality is somewhat compromised in a lot of cases on what you're going to do with it, especially if it's going to be exposed to, you might say, a conventional environment. PLA doesn't like moisture. It doesn't like heat. So, however, legacy materials, and those are the legacy materials that we have from injection molding that are so used. We see a lot of ABS. We see a lot of nylon. We see a lot of polycarbonate. But you got to remember, within those classifications in the injection molding worlds, there's thousands of different mixes, thousands of different materials. Well, we're not quite there in additive yet. We got a lot more materials than we used to, but we don't have thousands to select from. But when you're dealing with certain applications, they have a legacy call out, especially military contracts, about what material you can use, what you do with it. Some of the testing and qualification of parts are done with legacy materials, and so it's very tough to transfer those certifications over to additive manufacturing. And there's a lot of widespread misunderstanding of certifications. So that's a whole different discussion, different day. But materials are such a vital part of your functionality of your part. You can't underestimate what and when. Just because you know that, example, the customer used Delrin in injection molding for his part, and molding Delrin is no small feat, but he may not need it. He may be very comfortable in an additive part that uses a high heat nylon. So there's a lot of trade-offs that you can do. And sometimes you don't know until you do further analysis whether the part will pass. So material selection in any technology, whether it be traditional injection molding versus additive, is a big part of your part prep. Material availability and what it does inside a mold and injection molding is something that only a skilled tool designer and your manufacturing engineer can really give you some guidance on, especially your flow characteristics. Like you don't want to put a boss in the middle of a high flow area in your part. But in additive, you have certain design rules that are not very well known. And many of them do mix and match from injection molding because it's what you do with the part that makes a difference on your material selection, not the part itself. It's you sell the hole, not the drill that makes the hole. It's what you're doing with the part that makes a difference on what types of materials. There may be call outs for ESD. There may be call outs for any weathering. You've got a lot of what the part itself is going to do for the end user. So material selection is a huge part that needs to be done with an eye on what you think it's going to do in injection molding is going to be different in additive. It's going to change in additive. It's not going to behave the same. Injection molding imparts characteristics to the piece based on the heat and pressure that are used on putting that part into a core and cavity. So you have to keep in mind that what you think may not be true in additive and vice versa. So a lot of times you can get away with different materials in additive than you can in injection molding and vice versa. So material selection should be talked about early on in your product life cycle.
I love this topic because I think it's something that comes up a lot. Especially Stanley Black & Decker has been around for quite some time. So a lot of the times if we're looking at maybe an additive solution, that's one of the first things we ask is, okay, why is something being made with this material? And 9 times out of 10, the person that made that decision is no longer with the company. We don't know why it's being made with that. We don't know if the hardness actually needs to be as high as it's being called out. So that's something we've really worked hard on trying to educate on is, okay, what are comparable materials that exist in the additive industry, and does that satisfy your need? And how do we backtrack and say, what are we actually looking to accomplish, to Barbara's point, as far as what is the end use application and what is the function of it, and can we get there with a new material that we've never even considered before? So I think that's something we live every day. So really educating and providing enough information to say if this is even a viable solution, should we try it out, is definitely something we consider when we're looking at if additive is a good solution and is a material available that would apply.
Yeah. And now for one of the most important parts, something we haven't really talked about yet, quality. Quality is essential from the beginning. I think we both agree in keeping it in mind. But how do you think industries, companies particularly, are ensuring that their additive manufacturing production is going to keep up with conventional production quality requirements and regulations?
I think heavily regulated industries are really paving the way for how additive is viewed in production environment, because industries like automotive or aerospace, they already have really stringent callouts of what is appropriate, of what the right procedures are to be. So using that as a starting point, where if you're satisfying those callouts, you'll be fine in any other industry utilizing additive. So I think that's where we started, as far as where are we going to look to utilize additive and how are we going to test quality with that, is how do we make it really robust, and then we can work our way back based upon the needs of the application or the industry. But I think really the aerospace and automotive industries have done a really great job defining what quality needs to be. So using that as a starting point is how I think about it.
There's still work being done on a couple of the main factors that we run into in additive, and that's reproducibility of the part across the build bed. That's one of the things that I think almost every manufacturer is dealing with on the machine side, is to make sure you have a reproducible part first time, every time, not only from build to build, but within the build, if you're doing quantities. And so that you want to be able to have linear predictability on what you're going to get out of your machine, whether it be in the front right-hand corner or the back left-hand corner. You want to have predictability, reproducibility, and a confidence that your machine is going to produce the same part each and every single time. And it is a lot better than it used to be. It still needs to be a little bit better across the universal constraints of all equipment, and I've worked with so many of them. The other area that I think is largely, you might say, not as understood as we'd like, is that material itself in the production industries varies tremendously. You have melt indexes that typically have a range. In additive, we have a much smaller range that we typically use versus production methods. So because we have such a smaller melt range, or whatever, a smaller indices on what we're doing with the material, whether it be a thermoplastic, a thermoset, or a metal for that matter, we have additional cost on those materials versus typically production materials, because we have to control the quality of them so much better. So if you go to an open materials platform, for example, you have to recognize that there's oftentimes associated cost with machine setup, both in metals, thermoplastics, and thermosets. So that's what you get. That's a bit of a trade-off in terms of quality control measures on the material side. On the build side, especially if you're using open platform, you may also have some variability that you can dial out of the machine, but you need to be aware that it's not going to run the same time every time from batch to batch of material. That's the same thing true of injection molding. You change one Gaylord out for another Gaylord of the same material, even if it's in the same batch, you're going to have some variability depending on that place in the production area. So quality, we always look for the zero variability in the quality. We always want to use the Deming method where we have a really dialed in process and we have zero variability. We're still getting there. We're not there yet, but we're still getting there as an industry, both in production methods such as injection molding and in additive manufacturing. So variability affects by material, processing conditions, as well as equipment used, as well as the conditions that the part is going to be subject to.
Perfect. So we're almost out of time. I think we got, I don't know how long we have. Lindsay can haul that out. But we do have 3 questions in the Q&A. Joelle, Barbara, you guys should be able to access that. The first one is, where do you think design tools come into play as you are designing for different industry needs?
My first thought with that question is, the different CAD softwares that are available. And I think utilizing whichever software fits for that industry is going to be critical for adoption into the different businesses that are trying to drive additive manufacturing as a solution, because you don't want to be utilizing a software that, first of all, no one knows or they're uncomfortable with, because you're trying to make additive as agreeable of a solution as possible when someone's never used it. I think there's a lot of opportunity to break into that space of software to make it as easy as possible. And especially going back to what we were talking about before about labor, there's an immense amount of labor necessary to create CAD models, and that's not necessarily a skill that everyone has, and it's very time consuming. So having a software that would automate more of the design process and designing for different industries, I think would be something really great to see in the future to drive that adoption further.
Which also dovetails into the second question, which is interesting. I'll go into the second question in here. What are the most used automated solutions for AM? And what areas of AM process are most valuable for automation? I'd say 100% of the process, but that's impossible.
Yeah. I have a lot of experience in what we call mass finishing. So in the jewelry world, as you can imagine, you want your part to be sparkly and smooth. So something that we talk about a lot is how do you finish the part without ever having to touch it. And there's a lot of automation solutions that are already available and have already existed for many years. So understanding those technologies and utilizing them for the different additive solutions out there is something that we look into a lot.
And ironically, is the one with the most man hours, oftentimes, not all times.
Mm-hmm. Yeah, doing that automation on the post-build processing. And I note there's a difference between post-finishing and post-build processing. Support removal. If you can automate support removal, you typically cut a tremendous amount of time off your additive. If you don't have any support removal process, it's extremely time and precision oriented. And then the post-build finishing, the finishing of it. Just like if you polish an injection molding tool, it takes a lot of time. But if you polish a part that's going to be used for whatever reason that you're doing polishing, or you're doing coating, or you're doing some other type of post-build finishing, it's usually manual, and it usually takes a lot of time, and it usually adds a tremendous amount of cost. So yeah, I totally agree with you. Post-build is where the automation really can help. I do hope that there, I know that many of our audience in the Women in 3D Print world also run into inventors. And one of the things, a central question is make sure that they have a CAD file. But if you don't have a CAD file, make sure you charge them to make one because that's a real expensive process. So they don't have a file that you can print, garbage in, garbage out, or they don't have a file. It would be nice to have a file that can go directly into your machine. But if you have to create it, it takes a lot of time. So if you have a customer that wants you to quote something, make sure that they have a file that you can actually quote from.
And thank you, Barbara, for that. These are all great points. We have one last question. Barbara, this one's specifically for you. Do you think material characterization is important, and does that help before getting too far into production? I think I know your answer, but I'll let you.
Well, I think material characterization is important. The question is, how much do you want to devote to doing that? And that you can dial in the materials forever, but you have general classifications of material that are probably most appropriate for a certain type of application. So before you get too far into the weeds, you make your material section and you go up. If you have factors that affect which material that you're going, in other words, if you need to have a filled material so that you have less deflection, you're going to know that up front pretty much. You're going to know that before you go into production in most cases. But you don't want to find out after you go into production that your part flexes too much because you had design that didn't get done. So material characterization dovetails with your design. And that helps before you get into production, because otherwise you have to redesign the tool. You have to redesign it for different materials. You can't run, for example, a syringe out of a mold. You can't run it out of polypropylene if the mold was done, a cylinder was done in, example, in polycarbonate. It just doesn't work very well because you don't have the same material flow. You don't have the same material characterization. You don't have the same release and shrinkage. So it helps. It is not the only thing you have to do, but you have to know your material character that affects the part before you go into production, else you're going to have to go back and redesign your tooling. As well, in additive, many times you'll have to adjust your build patterns in your additive if you're doing FDM type building, or if you're doing a laser-based method, you have to look at where you have cross sections that are good. So there's a lot of design factors and application factors that you have to get into.
So much. Joelle, anything else to add?
I don't think so. I would like to add the Stanley Black & Decker team is definitely going to be hiring this year. So if you're interested in any of our open positions, please message me on LinkedIn.
And I believe we will be around for the networking session that follows. So thank you, Barbara. Thank you, Joelle, so much for participating in this panel. Really appreciate it.
Thank you.
Pleasure to be here. What a nice team, a nice group of people to be a part of. And thanks to everyone that attended. It's awesome.
Thank you so much.
Thanks.
Wonderful. Thank you all so much. Again, like you said, we're going to jump to networking, and I look forward to talking with all of you more on the networking stage. Thank you.